Welcome to the second lecture of the third week of the MPP math class. This lecture focuses on logarithms. We'll start off just by reviewing a little bit of background information you need for logarithms. The first is to talk about exponential functions. So exponential functions are any function where you have the x in the exponent rather than in the base. Notice that this function we have here, f of x equals a to the x power, is fundamentally different than a function like x squared or x cubed, a power function, because we have the x in the exponent. So if we're trying to solve for x, what we really are doing is, or what we really need is to get the x out of the exponent in order to do the algebraic manipulations we already know how to do. For exponential functions, the domain is defined as the real numbers, but the base of the exponential function can only be positive. It's worth at this point noting, taking a moment to talk about the special number e, which you've probably seen or heard of before. E is sort of like pi. It's a constant that seems to be a fundamental concept for a number of economics and finance settings. So the actual value of the constant, it's an irrational number that rounds to 2.71 or so. And formally defined, it's the limit of 1 plus 1 over n raised to the nth power as n approaches infinity. In your classes at Harris, you're likely to see the function e to the x, either in the context of talking about compound interest, or and when we're talking about discounting, which is the idea that when we're thinking about our utility over things in the future, we probably want to count periods in the future less heavily than we count the present period or nearby periods of the future. So we use the function e to the x in a number of those kinds of settings. We'll see that there's a special logarithm that is used to unwrap e to the x functions. So logarithms are, at their very most basic level, inverse functions. We have a function a to the x. We want to get the x out of the exponent. Algebraically, the thing we need to do is we need to take the logarithm of base a of a to the x. And the logarithm base a of a to the x is equal to x, because logarithms are the inverse functions of exponents. Similarly, we can take a raised to the power log a of y, and it will produce the value y, because inverse functions work in both directions. Logarithmic functions are defined where x is positive. The base of logarithmic functions can be anything on the positive reals except the number 1. And the reason for that is that there is not a unique solution to the problem 1 to the x in any context, because 1 to the 5th is equal to 1 to the 10th. And so you end up with what's called a correspondence. There are some mathematical properties of logarithms that it's probably worth simply memorizing. The log base a of 1 is equal to 0 for any base, because a to the 0 is equal to 1 for any base. The log base a of a is equal to 1, because any base raised to the power 1 is going to be itself. The third property is simply this inverse property we were talking about, that the log base a of a to the x is x, because the log conceptually is the inverse function of the exponential function a to the x. In fact, I find that if I have trouble remembering how to make my logarithms work out correctly, I fall back on this inverse definition, that I remember that the logarithm will unwrap or undo the function a to the x and give me back x, and then I can work forward from there. The final property is that if you have the log base a of a to the x and know that it's equal to the log base a of a to the y, you can immediately say that x and y are equal to one another, which grows out of the fact that if a to the x is equal to a to the y, you know that x and y are equal to one another. Logarithms are something it's easiest to see through examples, so we'll go ahead and do a few examples at this point.
So we'll start with the basic and move to the more complex. You might, for example, know that the log base 2 of 3 is equal to the log base 2 of x, and you're trying to figure out what the value of x is. The good news here is that there is a unique value for which this is true. You have the two of the same logarithms, and the only scenario where that can be true is if x is actually equal to 3. You might, in a different scenario, be trying to solve what is the log base 4 of 16. And basically what you're asking is, if I take the log base 4 of 4 raised to what number is going to be equal to 16? Well, 4 squared is 16. And now what we know is that since the bases of the logarithm and the exponent are the same, and since logarithm and exponentiation are inverse functions, that in fact this log is just extracting that exponent 2. Finally, in some cases, you might have a situation where you do not know the base of your exponent, or of your logarithm, and you are trying to solve for it. If you stop for a moment and ask, sort of, what does this equation say? What it is telling you is that x squared raised to the second power is equal to 36. So in other words, I took the base, I raised it to this squared power, and I know that that's going to be equal to 36. So at that point, it's probably pretty straightforward for you to recognize that x will be 6. So now we'll work through a few actual examples to solve. If we have the log base 2 of 64, what we need to think through is what value 2 raised to what power is equal to 64. It may help you to remember that 2 cubed is 8, and 8 squared is 64. So 2 raised to the 6th power is the same as 64. And now it's a straightforward matter to extract the 2 and get back your exponent 6. If we have the log base 4 of 1, what we're asking is, we have the log base 4 of what 4 raised to what number is going to be 1? Well, 4 raised to the 0th power would be 1. And now we can extract our exponent because the base of the exponent and the base of the logarithm are the same. So the log, in fact, of any base of the number 1 will always be 0. The log base 2 of 2 is again straightforward. We know that 2 raised to the first power is equal to 2. So we get the exponent back, since the base and of the exponent and the logarithm are the same, and we find that the log base 2 of 2 is equal to 1. And this problem is basically the same sort of a thing. We recognize that we have a special name for the log base e. We call it the natural log and write it ln, and that the natural log of e is simply equal to 1. So now we'll do a few examples where we're using the definition of the inverse function just in the opposite direction. So here we notice we have 10 raised to the power log base 10 of 3, and since the exponent and the logarithm are inverse functions, we get back simply that the 10 raised to the log base 10 of 3 is simply 3. Similarly, if we have 3 raised to the log base 3 of 8, it will be simply 8. So the inverse functions are canceling one another out, and we're getting 8 back. If we have e raised to a natural log, similarly those will cancel one another out because the base of the natural log is e. And working in reverse, if we have an unknown up in the exponent, our log of the exponent of x plus 5 will simply be x plus 5. And in the opposite order, e raised to the natural log of 1 minus x will simply be 1 minus x. So in all of those cases, we're using the fact that the exponent and the log are inverse functions from one another.
You'll see more about this in the next lecture regarding graphing, but I think it's useful to show right now that the inverse functions 2 raised to the x power and log base 2 of x are actually just reflections of one another about the 45-degree line. So that you see that if you folded your screen in half at the dotted line where x is equal to y, the two graphs would perfectly line up with one another. If you have a function that is just a logarithm of any base, it will extend down towards infinity for values of x as they approach 0. And it will always go through the point 1, 0. Similarly, if you have the exponential function, like 2 raised to the x power, it will always extend out to negative infinity for values of y close to 0. And it will always pass through the point 0, 1. Now, when you're doing algebraic manipulation using logarithms, there are some additional tools or tricks that you can use. The first is what's called the change of base, and what it allows you to do is to take the logarithm with a base of a and convert it into a logarithm with a different base. You might wonder why that would ever be useful. What's going on is, if you can see that the value of x is something raised to a particular power, but the base is different, you can use the change of base to get out that power that you want. So, for example, if you have the natural log of x, you can convert that into log base 10 by taking the log base 10 of x divided by the log base 10 of e. Similarly, if you wanted to convert it into log base 4, you could take the log base 4 of x divided by the log base 4 of e. And then you could just calculate out the value in the bottom, and you might be able to get rid of the logarithm then by if x, for example, if x were 16 in this case, the log base 4 of 16 is going to be 2, and so that would let you unwrap the logarithm and get a non-logarithm value back out. Just to do one more example, if you have the log base 4 of 8, 8 is equal to 2 cubed, so you might want to convert it into the log base 2 of 8, and so from that you can see the log base 2 of 8 is actually the log base 2 of 2 raised to the third power over the log base 2 of 4, and we know that 4 is simply 2 squared. So then the numerator and the denominator the logarithms can be gotten rid of easily through this change of base formula. If you have the logarithm of a product, so two values multiplied together, like log base 8 of u times v, it's going to be equal to the sum of the separate logs. So if you would take log base a of u plus log base a of v. I want to tell you to be very careful right now. There is not a good way to get rid of a sum. So if you had the log base a of u plus v, you can't do anything with that. You cannot remove the logarithm or split it up in any way. So in this case, it only works for a product or a quotient, that you can split up a product. So in this case, if we have the log base 2 of 14, we could split that out, since 14 is the product of 2 and 7, into the log base 2 of 2, which we know is 1, and then the log base 2 of 7. The quotient rule is basically just the product rule with one addition. It's recognizing that the power on v in the bottom in the denominator here is actually -1. So just like when we were dividing exponents, we needed to use subtraction. We'll do the same thing here. So if we have the log base a of quotient u over v, that's going to be equal to the log base 8 of u minus the log base a of v. To do an example, if we have the log base 4 of 1/2, that would be the log base 4 of 1 minus the log base 4 of 2. The first value, log base 4 of 1, is always going to be 0 regardless of the base. The log base 4 of 2 we can unwrap a little bit more by converting it using the change of base formula to the log base 2 of 2 divided by the log base 2 of 4, which we know is the log base 2 of 2 squared. So that would finally give us the value -1. Take a minute to work through that example on your own at this point if you didn't follow as I was talking along. The power rule is honestly the thing that I use the most when I'm dealing with exponents, because remember, very often the problem is that we have a variable up in the exponent. So in this case, if we have the log base a of u raised to the n power, we can get rid of that n entirely simply by moving it to the coefficient in front of the logarithm. So to give you an example, the natural log of 9 is going to be equal to the natural log of 3 squared. And then we can take that exponent 2 and move it to the coefficient in front so that we have 2 times the natural log of 3. The log base 2 of 8 is the log base 2 of 2 cubed. So we take the 3 in the exponent, move it to the coefficient. We get the log base 2 of 2 times 3. The log base 2 of 2 is 1. So we simply have the number 3. Finally, if we have the natural log of e raised to the 4th power, we can bring that 4 in front as the coefficient. We get 4 times the natural log of e. And remember that natural logs are simply logs using the base number e. So natural log of e is going to be 1. So now on to some examples.
All of this machinery we've been working on about logarithms is really about solving equations where logarithms are useful. So for example, if you have a function, or if you have an equation where e to the x is equal to 26, and you're trying to solve for x, you need to get the x by itself. The only way to do that algebraically is to apply the inverse function. So since the natural log of the exponent is the inverse function of the exponent, we will take the natural log of both sides. And just like it's okay to multiply both sides of an equation by the same number, it's okay to take the logarithm of both sides of the same equation. So on the left-hand side here, the natural log and the exponentiation will cancel one another out, and you will be left with x is equal to the natural log of 26. So really all of the rules that we've been working on up to this point have been getting us to the place where we can solve this type of equation. Of course, in real life, you're more likely to see a more complicated function like we have here. In order to combine the x terms, we need to simplify this e to the 2x into something times e to the 2x. There are several different ways to do that. Probably the easiest and most straightforward way is to realize that from our old rules from exponents, we know that e to the x squared is equal to e to the 2x. So if we take, we can substitute e to the x squared into this equation for e to the 2x. we're now left with a quadratic of the form e to the x squared minus 3e to the x plus 2 is equal to 0. And while we in this class haven't talked about factoring polynomials, you've definitely seen it before. And the thing to realize is that you can factor e to the x just like you would any variable y or z or x. So in other words, we can split this into two terms that are being multiplied together in order to find the roots of the function. In the first slot for each, we will put e to the x so that we get this e to the x squared term. And then we need to ask what two numbers can we multiply together to get positive 2, but add together to get negative 3. And hopefully you see that negative 1 times negative 2 will be positive 2, but negative 2 plus negative 1 would be negative 3. So in other words, this equation has two different roots, one where e to the x is equal to 1. So we would use the natural log to get the x by itself, and we need to apply the natural log to the other side of that equation so that we get that x is equal to the natural log of 1. Or we have e to the x minus 2 equals 0, which is the same as saying e to the x equals 2, which simplifies in the same way to be that x is equal to the natural log of 2. So there are two possible solutions to this equation. Notice that we should probably simplify the first one. The natural log of 1 is always going to be 0 because any number raised to the 0th power will be 1. Our approach to solving equations involving logarithms is very similar. So if we have that the natural log of x is equal to negative 2, we can get rid of this natural log in front of the x by exponentiating both sides. We get the exponent we get e to the natural log of x is equal to e to the negative 2. These the e and the natural log cancel one another out. X is equal to e to the negative 2, or we could also write that 1 over e squared. In another example, if we had something like 3 plus 2 times the natural log of x is equal to 2, we're going to get x by itself, so we'll move 3 to the other side and then divide both sides by 2. We would get that the natural log of x is equal to negative 1/2. And then we exponentiate both sides, so we get e to the natural log of x is equal to e to the negative 1/2, which translates into x is equal to 1 over the square root of e. As our equations get more complex, there are a few tricks that we can use to work through the problems. So the first thing to recognize with this particular equation is that we are adding two logarithms together, both of which have the same base. And if we remember back to the product rule, we know that that means we can simply take the logarithm of the product of those two things. Now it's a little less clear what to do with the right-hand side of this equation, but one thing that you can do is recognize that the logarithm base 2 of 2 is equal to 1. And so that's another option, so that you can then get rid of both logarithms on both sides and say simply that x plus 1 times x is equal to 2. You can expand that out and move the 2 to the other side so that you get x squared plus x minus 2 is equal to 0. You can factor the polynomial x times x, and you're going to ask for what numbers, would I be able to multiply two numbers together and get -2 and add the two of them together and get +1? That would be x plus 2 and x minus 1. Normally, if we had this problem, we would then immediately say, well, I can take x plus 2, set it equal to 0, determine that x is equal to -2, and also take x minus 1 equal to 0, conclude that x is equal to 1. There's one more thing that we have to do with these logarithm equations, though. Notice that we are taking the logarithm of x, and we're taking the logarithm of x plus 1. So both of those values have to be positive, which lets us eliminate the second choice, and we're left with a single solution that x is equal to 1. Here's another problem that would use a very similar technique with the quotient rule. This is probably a good time for you to pause the video and try this problem on your own. In order to solve this problem, we use the quotient rule because we have this subtraction. What we see is that the natural log of x over x minus 1 is equal to, and now I'm going to try and get a natural log on this side. The natural log of e is going to be equal to 1. So in other words, we have e is equal to x over x minus 1. We can distribute the x minus 1 to the other side, times e is equal to x. We multiply out. We get that e to the x is equal to x plus e, and moving the x to the other side, we get that e to the x minus x is equal to e, and finally we pull out the x, e minus 1 times x is equal to e, and get to that x is equal to e over e minus 1.